Logan. Hi, Logan. Do you hear me?
Yep. Hey guys, how's it going?
All right. So I think we're good to go. So just Logan, please go on with your presentation.
Okay. So like Peter said, this is a preview of the presentation that we'll be giving at a conference in Paris, the ETHCC conference. And it's going to be a deep dive into some of the technicals around the Ethereum Alarm Clock, and which is the protocol that we're building the Chronos app on top of. So the Ethereum Alarm Clock is a smart contract protocol that's built on top of Ethereum. And it was created by Piper Merriam in 2015 to fulfill the purpose of scheduling transactions to be executed in the future. The protocol's had a long history. It's been operational at various points. During most of 2017, it wasn't working. So we started up the development again around late 2017. I've been working on it for about 4 or 5 months now. It took a couple months to get working, but we have it on Kovan. We've been testing it and running it. We're looking to get some audits done soon and to put it on the mainnet and open it up to public use. So here's a cool bit of history. Piper Merriam, the creator, who's now at the Ethereum Foundation, giving a talk at DevCon 1 about the Ethereum Alarm Clock. So the reasons behind the Ethereum Alarm Clock are kind of simple. It's simply that there's no native way to schedule transactions on Ethereum. Yet scheduling transactions is something that people have taken for granted with modern web applications. So Ethereum, all transactions require someone to be sitting at their computer and to actually trigger this execution. And of course, people have gotten used to just being able to say when they want something to happen, and having every execution being triggered seems kind of like going back into the past a little bit. So the Ethereum Alarm Clock is a way to bring the Ethereum blockchain closer to what we expect for modern day usage. And that simply just means being able to schedule transactions on chain in a trustless way. So to kind of explain a little bit more why this is a problem that needs to be solved, I'll talk about the two types of accounts we have on Ethereum. So we have users, which control a private key and are the ones who actually execute the transactions. And then we have smart contracts, which are deployed blobs of code that have logic contained inside of them. And when they're triggered, they'll execute this logic. So what the Ethereum Alarm Clock is trying to accomplish is to make smart contracts which are unable to execute themselves, able to be scheduled and execute without a user sitting there to execute them. And so we're going to go into a deep dive of some of the technicals around the alarm clock. First, I'll kind of give a high-level overview of the architecture, and then we're going to dig into the code and really get nitty-gritty into it. So here's a high-level overview of how the Ethereum alarm clock architecture and flow works. On this left-hand side, we have the user scheduling a transaction with the alarm clock protocol. This deploys a transaction, which is its own separate smart contract with all of this execution logic coded into it. On the right-hand side, we have the time nodes, which are these executing clients that people will run in this marketplace type of environment, which I'll go into in a little bit later. And these time nodes will be watching the blockchain for upcoming transactions and will automatically execute these transactions on behalf of the user who has inputted all of this scheduled parameters. When the time node executes this transaction, it gets rewarded with a bounty, and the execution gets sent to its destination. The alarm clock protocol consists of a few different smart contracts. I think it's about 20 smart contracts in total. But we can subdivide this into 4 major categories. On the left, starting on the left, we have the schedulers, which are the top level APIs to input parameters. And these contracts talk to the lower level request factory, which are the contracts that actually create the new transaction requests. And the request tracker then keeps track of each new scheduled transaction. And on the right-hand side, we have the transaction request core, which contains all of the logic for scheduled transactions in a central smart contract. We do this because we're going to be deploying transaction requests often, every time someone schedules a transaction. And we don't want all of that logic to get deployed because it's costly. So we use the request factory to create just a wrapper transaction request, which simply delegates the call to the transaction request core. I'll go into that a little bit more later. And here's another way to kind of view the architecture. You can kind of look at the scheduler as like the tip of the pyramid, the exposed point, with the request factory a little bit lower down, and the whole thing built on a whole slew of library contracts. So I'm going to get into the scheduler, how it works on a technical level, and the parameters that it takes. So there's 2 varieties of the scheduler for the Ethereum Alarm Clock. One that works with block numbers and one that works off of timestamps. So depending on when you want your transaction to be executed, you might want it at a specific block number. Let's say block 6,500,000, or maybe you want it at a specific time, and in that case, you can instead use the timestamp scheduler. So here's the scheduler interface, the code for the scheduler interface. What I want to point out here is one that it really doesn't have much logic to it. Like I said, it is kind of just the entry point for the rest of the smart contracts. It has the main schedule function, and this takes 3 parameters, one address for the recipient of this scheduled transaction, some bytes, which will make up the call data, and then an integer array of 8 integers. And these are the parameters that will actually be executed when this scheduled transaction is called. So here's some images which show the parameters for the scheduling. We have the gas and the gas price, the call data. What I really want to point out here is the windows for a scheduled transaction to be executed. So there's a few different phases in the life of a transaction request. It starts out when it's deployed in a claim window. And during this phase, the time nodes can actually send a transaction saying they want to claim the future execution of this transaction request. And to do this, they send a small deposit, and they and they're saying they guarantee that they will execute this claim transaction, or else they'll lose that deposit. Straight following the claim window, there's a brief period of time where nothing can be done to a transaction request. It can no longer be claimed. It can no longer be canceled. It's just frozen. This is to help guarantee that the transaction request will, one, be executed from the time node side, and from the scheduler side, that it will no longer be canceled. And then after the freeze window starts the execution window. The first part of the execution window, however, is reserved for the time node which has claimed it. Like I mentioned before, if the time node that has claimed the transaction request does not execute it, it'll go into a free-for-all execution window where any time node can execute it. And in this case, the claim deposit gets rewarded to the time node that executes it. And here's the parameters broken down. So we have the call gas, which is the amount of gas that will be sent with the transaction. The call value, which is the amount in Ether or Way that will be sent with the transaction. The window size, so this is the execution window I was talking about on the previous slide. It can be as long or as short as you'd like. It's generally recommended not to make it too short, just because the way the alarm clock works, it's hard to guarantee an exact block. A block range of about 20 blocks seems to be about the minimum. The window start, which is the either block number or timestamp, which the execution window will start. The gas price that'll be sent with the transaction. This can be tweaked depending on the network average, or whether or not the person who's scheduling the transaction wants the transaction to be prioritized over other ones. And then we have the alarm clock fee. This will be sent to the alarm clock protocol. It's an optional parameter, so it doesn't always need to be set. We're thinking it'll be used by organizations who choose to incorporate the alarm clock into their interfaces. And then we have the bounty, which is the reward that is given to the time node for executing a transaction. This is a really important part of what makes the alarm clock crypto-economically sound. I'll go into that a little bit more toward the end of this presentation. And then we have the required deposit. I was referring to this earlier as the claim deposit. It's the amount that needs to be sent by a time node to claim a transaction. So a little bit lower down underneath the schedulers is the request factory. This is the contract which actually pumps out the new transaction requests. Like I said, each new transaction request is its own smart contract. So this is good for a few reasons. One reason being security. So there's no one central big honeypot where funds are stored. So it's distributed throughout each transaction request instead. So each contract will only hold the funds that the user has sent to it. And it's just a little bit safer for in case of vulnerabilities or unforeseen situations. And the really cool part about the request factory is that it's built off of this clone factory pattern. So each transaction request smart contract is actually just one function. It's just a fallback function. And what that fallback function does is take the data it was sent and routes it to the transaction request core contract, which contains all the logic, via delegate call. And what this does is it saves the amount of the size of the contract when we're deploying it. So it cuts down the gas cost of deployment. And we got it down from 2.5 million to just under 1 million gas, which is still kind of high because the transaction requests use a lot of storage, but it's a significant drop from where it was. So here's the interface for the request factory. It consists of 4 functions. One function to create new requests. One function to both create and validate a request. The function to validate requests, and a function to acknowledge whether a transaction request was created through this request factory. So it's actually kind of interesting. You might notice that there's 2 functions to create requests, one to create a request and another one to create a validated request. So they both really accomplish the same thing. One is just a little bit safer to use, but they're both exposed publicly. So if you want to make sure your request is valid when you send it, you'll always want to use the create validated request. I don't think you'll want to use the create request because it doesn't do the validation and your request might not go through. So let's talk a little bit more about the transaction request contracts. So like I mentioned before, each contract is its own smart contract. It'll delegate all the calls to the core contract, which contains all the logic. And it holds the funds, which will be paid out to the time node when the transaction gets executed, as well as the funds that will be sent to the transaction, to the funds sent during the executed transaction. And one really cool thing about the transaction request contracts is the proxy function, which opens up the possibility of doing things like buying tokens from ICOs using the alarm clock. And I'll talk a little bit more about how that works in a couple slides. So here's the contract interface for the transaction requests. There's a group of primary actions to execute, cancel, and claim. These are actions that will be taken by either the time node or the user who scheduled this transaction. The time node will claim or execute transaction requests, and the user who scheduled the transaction can call cancel either before the freeze window or after the execution window. Here's a proxy function. Couple functions that will return data. These are mostly useful for clients if you're looking to either build a web app or build a client. And then there's ways to pool payments from this contract. So in the event that something goes wrong, the payments won't actually be stuck. You can call these functions down here and bring the payments out. And so the proxy function is a pretty cool thing. What it lets you do is send a transaction using the transaction request contract as the calling address. So one of the primary things here is to call this to transfer tokens or maybe non-fungible tokens like collectibles. So what this does is you give it the address to send to and the call data, and it'll send that call data to the recipient address, and if that call data matches one of the functions on the recipient smart contract, it'll call that function and then execute all that logic. So to send tokens out of this, you would pass it the data to call a transfer function on a token contract. And here's the executing flow. So after a transaction request is deployed via the Ethereum Alarm Clock contracts, it'll wait to be executed by a time node, and there's guarantees that it'll be executed as scheduled. Here's the execution data. We can see that the data that it uses to execute is the to address, call data, call value, call gas, gas price, which again, these are set by the scheduler. They go into a smart contract. There's no way to change these. There's no way to block these. That's one of the big things about the alarm clock contracts, is that it guarantees that the exact way you specify your transaction to be sent when you schedule it, that's the way that it will be executed. All right, and so I've talked a bit about the scheduling side of the protocol, but now I want to get a bit more into the executing side. So we call the executors time nodes, and these are people who are running clients or servers off chain that are constantly watching the alarm clock contracts and for new transaction requests, and will then take the actions to either claim or execute these. So this is the way that we get the effects of not having to always be there to execute your transactions on time, but rather we use the time nodes as the way to guarantee that the transaction will be executed. So it's completely free and open to everyone to run a time node. If you are technical, can use a command line. You're able to run a client. We're building a web application, so if you hold day token, you can actually run a client in your browser, which is really cool. It makes it so it's a lot easier to be a time node, and and these time nodes will be rewarded the bounty every time they execute a transaction. So it's almost always hopefully will be profitable for these time nodes to run. And so we expect a competitive market of many people running time node clients to execute transactions. And so this bounty is what guarantees that the transaction will be executed and that the protocol is crypto-economically sound. So crypto-economics, for those who aren't so familiar, is kind of this emerging field of getting certain kinds of behaviors, desired behaviors, via using incentives. So the way that the alarm clock uses crypto economics is to incentivize people running time nodes, which will guarantee that transactions will be executed as they're scheduled, which then gives us the effect of being able to just schedule a transaction and know that that transaction will be executed. So exactly how that works is with the bounty. Each time a time node is executing a transaction, it'll be rewarded with the bounty plus the gas that's used. So at the very least, the time node won't be using any funds because it'll always get reimbursed at least the gas funds that it uses to send a transaction. The bounty can be set by the scheduling user. It can vary between really low, if maybe you're pretty sure there's a lot of time nodes out there, or if you really want this transaction to go through, you can set it really high and be pretty confident that a time node will want that bounty and execute your transaction. Another thing we've been working on, I've been working on is the Ethereum Alarm Clock JavaScript tools, which I'm calling eac.js. So this can be kind of separated into three main parts. There's the JavaScript library, the JavaScript client library, which can be used, which is contains the logic for time nodes, and then the command line interface, which is a way to run a time node and to schedule a transaction. So these tools are written in JavaScript. They're available on npm under these names, depending on which one you want. The lib and client are more developer tools, whereas the command line interface is probably a developer tool as well, because it involves using the command line, but is more focused on being an interface to schedule and run a time node versus the client and the lib being libraries for developers to build on. So the command line interface is used to create a wallet, to schedule a transaction and run a time node. And I think I can give you guys a quick demo really quick. So here I am in a terminal. I'm running Coven with parity, and I'm all synced up to the latest state of the network. So I'll show you using eac.js to schedule a transaction. The S is short for schedule, and we specify that we want to schedule a block via block numbers. And this might be a little bit slow. If this is too slow, we'll go ahead and just move on. All right, there. It was a little bit slow, but I'll try to get this through. So it asks for all the details about scheduling a transaction. We're just going to go ahead and push through all the defaults. These are the parameters I went over earlier in the presentation. It'll ask us if we're sure about all of this. It'll tell us the endowment, which is the amount that needs to be sent to cover all of the costs. We say yes. And it'll send this transaction to the blockchain. And once that transaction is mined, it'll give us the transaction hash and the address of our new transaction request. So if we take this and look into Etherscan for the Coven network, we can see that indeed it got mined. It transferred the funds through the scheduling contract, the request factory contract, and finally to the transaction request contract, which is newly created smart contract owned by the person who schedules the transaction. And we can either cancel this if we choose we don't need that transaction to be executed any longer, or for a time node, which I'll show you next, we'll be looking out for this to either claim it, if we can claim it, or execute it. So let's see if we can run a time node here. So again, we're using eac.js. We specify C for client, and we tell it to auto start. Oh, oops. I think I'm using an older version, so it doesn't have the auto start yet. And it'll say, welcome to the Ethereum Alarm Clock client. It'll tell us the account we're executing from, how much Ether we have, and now we tell it to start. We can open up the logs down here. They'll be available on your home directory if you're using Linux or Mac. And they're available under eac.log. So we can see that this client now has found the transaction request at address 83D244. Let's check. Yep, that's the same one that we just scheduled. So now we'll let that client run, and in a little bit it should have executed that transaction. We'll check back on it in a few minutes. So in the meantime, I'm going to really give a broad overview of the other tools available with eac.js, which is the client package. We're using this at ChronoLogic to build the time node in a browser. And it's available for other developers to look into, to see how it works, to maybe use if they would like to. And then we have the lower level lib, which is the low level wrappers over the contracts, which make it really easy just to get up and running with the alarm clock contracts without having to do a ton of boilerplate code. And to illustrate this, I'll give you a quick example. So if you've used Web3 before, you'll recognize these first 3 lines. It's just instantiating a new instance of Web3 using a provider that we have running on localhost. So after we do that, if we want to use the Ethereum Alarm Clock contracts, we can use eac.js -lib, and we pass in that Web3. So passing in that Web3, what it does is it'll read what chain the Web3 is initialized on, and it'll automatically use the latest contracts for that chain, for that network. So whether that's Coven, which is what we're using now, or potentially other test networks, or the mainnet soon in the future. And then here's just a quick example of how we don't need any boilerplate to actually use these contracts now. We just tell EAC that we want the request factory, and right away we just have access to it without having to give it an ABI or any of that boilerplate. We can call get requests. This will give us back a list of transaction requests. This is a block in the past, so this you would have to change this block number. But we can take that first transaction request, this in this array, call it my request, and create a transaction request wrapper from that, which will let us execute that transaction request, or call its data, or claim it, or anything else. We just have these functions available to us right away. So we take what would be a lot more boilerplate and just turn into really simple declarative way to interface with these contracts. All right, and so I'm going to give you guys a demo of using the web app we built. Right before I do that, let's just check the command line really quick. We see down here that we attempted an execution of that transaction request, and we succeeded and executed that transaction request. So just to make sure that everything happened like it was supposed to, we'll type in get stats into this client, and we can get the stats. We'll see we claimed 0, we've executed 1 like we thought we had, and we've gained 0.15 Ether in the process. All right, so now that you guys have seen how to do that with the command line, I'll show you the web app way. So here's the web app. We have a few options here on the sidebar. We can schedule a transaction. We can view the transactions that have been scheduled. We can run a time node, and we also have links to the Debt Smart contract and the day token. So let's look into the transactions really quick at these completed transactions. So is this the same one? No, this is a so this is a different transaction that has been executed, or not executed actually on the status. But here we'll be able to see the transactions listed down here, along with the bounty and their values. And now I'll show you how to schedule a transaction. So with the command line, it was kind of prompting you for information all along. This way is a lot nicer to use. It's really intuitive. You can type in your time zone, type in when you want that transaction to happen. I'll bump this up a little bit to 9:55. Click next. We enter in the address we want to send to, the amount of Ether we want to send, the amount of gas, as well as the gas price. If we want to add in some custom data, we can right here. we'll choose not to require a deposit for now, and we'll set 0.1 Ether as a bounty. It'll ask us to confirm. We say yes. Let's schedule this. And it's loading. Should be just a second. And it should schedule this transaction in just a moment. We'll also go into the time node here, which is the newest feature that we're currently adding. Instead of using the command line interface, you'll be able to run a time node straight from your browser, as long as you hold day token. So as I showed earlier, the client should be profitable. So if you're holding day token, you'll be able to just come into here, start a time node, and plausibly start making some profit from executing transactions. So to wrap up, let's talk about some of the use cases that the Ethereum Alarm Clock has. So one of the initial big use cases might be buying tokens from ICO contracts. Instead of having to stay up depending on time zones you're in, or having to be at your computer at the exact moment ICO is open, what you can do is schedule that transaction. We might see some, we're hoping to see some ICOs maybe use this logic natively to instead of to actually just support having users schedule transactions instead of actually having to be there right at the moment. This is also a way to kind of pre-commit funds to an ICO as well. Besides that, we have any kind of routine payment, such as like a rent payment for an apartment or a phone bill, anything that you pay once a month. What you can do is you can just fund a wallet and schedule each of those transactions to happen on the first of the month or just every month, and then have the alarm clock execute those transactions for you. So it takes all of the it's a little bit more like what we've come to be used to now, with payments that just get pulled from our bank accounts. Now we can just fund a wallet and have those payments ready to be sent. Maybe the coolest part for developers is that this opens up a ton of smart contract integration and automation. So once we have the ability to schedule transactions for a point of time in the future, we now can start all kinds of cool things. Like we can have logic that either depends on something, a future transaction, or schedules a future transaction. We're working this into the debt smart contracts, ChronoLogic, and another cool example is the Ethereum Alarm Clock Canary, which was originally created by Piper, and is a smart contract that schedules a transaction to itself every 2 to 3 hours, and once that transaction gets executed, it will schedule another transaction. So it is a continuous feedback loop, and that's kind of just to make sure that the alarm clock is working as intended. And if each one of these transactions get executed, then we know there's time nodes running, and we know that the contracts are working as they should be working. On top of the actual smart contract level, we can start building client-side dApps with eac.js. So if you want to have a little bit higher level usage with this, if you want to just be using it in your JavaScript code and you don't want to write any Solidity, that's totally possible to do using the JavaScript EAC tools. And the last use case is, of course, running a time node. We anticipate this is going to be generate a lot of excitement because it's pretty similar to running a miner. The idea is that if you operate this node, that you'll be generating some profit for doing so, and you're not just doing it for free. If you're executing transactions, you'll be getting paid to execute those transactions. All right, and that concludes the presentation. I hope you guys learned a little bit about how the Ethereum Alarm Clock works on a lower level, and I hope you guys are excited for the upcoming use cases and the dApp.
Okay, thank you, Logan. That was really great, very in-depth explanation on how the Ethereum Alarm Clock works and what is the time node and why we need that. And maybe we could do like a small Q&A now. I see our guests on the webinar have questions, and basically one of many, like, many times repeated question was who decides on amount of the bounty, and how to basically set the proper bounty. So could you put a little bit more light onto this topic, Logan?
Yeah, sure. So the bounty is set by when you schedule a transaction. So it's one of the parameters that you'll input into it, as well as the call gas, the call value, the execution window, and so on. So you can set the bounty as high or as low as you'd like. Generally, if you really want this to make sure the transaction goes through, you'll want to set it a little bit higher. And this is what incentivizes the time node to then execute your transaction. So the bounty that you set will then get sent when your transaction is executed, and that's the profit that the time node is making.
Okay, that's great. So the other question that we saw many times was regarding the day token. So as you said, day token will be required in order to run the time node. And many people who hold the day tokens, they probably might be a little bit concerned about the security side of things of this. So could you explain, because we know that we have two separate accounts, the time node account and the day token. So could you explain why it is actually safe and doesn't really put any of your day tokens at risk?
Yeah. So the way that we're using the day token is actually we're using a kind of proof of stake mechanism where to run a time node, you need to sign a message that shows that you own these day tokens. And then the time node that you run doesn't even have to be the same address. So you can keep your day tokens in a completely separate address as long as you sign a message proving that you own those day tokens. You actually don't even need to touch those or send those anywhere at all. You can create a completely fresh wallet using MyCrypto, and then send that just a little bit of Ether, and to pay for gas costs right off the bat, and then you can use that new wallet to run a time node.
All right, awesome. So as you see that it's gonna be perfectly, secure. So we are not putting any of your data tokens at risk at all. So
Yeah, for sure.
thank you, Logan. So do you have anything else to add to our, community?
Just I would just say it's just really exciting. We're going to be giving this talk in Paris, and we're working really hard on the DApp to get it out, and we're hoping everything will be up and we'll have everything finalized and we'll have a release date for the conference.
Yes, awesome. So, any one of you from the community, if you would be by any chance in Paris, participating the conference, so just drop by into our booth. We will be there, and we can always answer your questions. We can discuss, potential new ideas, etc. So you're welcome, to visit us there. Okay, I think that's all. Thank you, Logan.
Oh,
That was really great.
yeah, one last thing. I just want to say that my email is here. If you would like to send an email to me, I'll try to answer any questions. I also included a link to the GitHub repos, both ChronoLogic's and the Ethereum Alarm Clock's repo for anyone who wants to look at those.
All right, awesome. Okay, so thank you guys, and have a nice end of, or have a nice Sunday. Thank you for your participation.
Thanks, guys.